Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's class. In last class, we discussed the time dependence of the wave function by discussing the time dependent Schroedinger equation. We discussed the stationary states and non-stationary states. We saw that we call a state stationary state when its probability density does not change with time. On the other hand, we defined non-stationary state where the probability density of the state depended on time. So, to discuss while discussing the non-stationary state, so this we obtain the stationary state when the spatial part of the wave function is an eigenfunction of the Hamiltonian, and we obtained the non-stationary state when we discussed about a state of the system when it is not an eigenfunction of the Hamiltonian. So, in that case this arbitrary function can be expressed as a linear combination of the eigenfunctions of time independent Hamiltonian. So, we have this expression when we write down the psi star psi, we would see that we will have first some terms which will be independent of time, and then we will have some other terms which would have explicit dependence on time. Now, in this case the probability density actually have explicit dependence on time, and to obtain this explicit dependence of the probability density on time, we must look at these terms carefully. And when we look here, we know omega n and omega m, they are actually the energies of the time independent Hamiltonian. Psi n and psi m are again the eigenfunction of the time independent Hamiltonian. What we do not know is what are these coefficients C n and C m. If we know these coefficients in the linear in this series expansion, then we would be able to get the stationary state we would be able to get the total wave function and its probability density as well as its time evolution or how it has explicit dependence on time. So, now we will try to see what are these C n or the coefficients that we have. To do that, let us do a little exercise. Let us first take one psi j function, which is nothing but one of the eigenfunctions of the time independent Hamiltonian. I multiply this eigenfunction with this psi, but not at time t, but at time t equals t 0, that means at initial time. So, in initial time I am expecting that I would know I would start the system at time t equals t 0, and then I would try to evaluate this overlap integral. To do this, so I have now this function is expressed in terms of this series. So, I can write this as a sum over C n, and I am integrating now this function . Now, look at this function. What I have is that psi j stars multiplied by psi n, I am integrating, and I have this time factor. See here it is minus I omega n t 0, t 0 is my initial time. So, therefore, when I look at this integral, I see that this is actually an overlap integral between two eigenfunctions of the same Hermitian operator. Psi j and psi n are simply two eigenfunctions of the time independent Hamiltonian. So, therefore, they are orthonormal to each other because Hamiltonian is a Hermitian operator and the eigenfunctions of the Hermitian operator are orthonormal. So, therefore, since they are orthonormal, this sum where I have n number of terms, I will actually be left with only one term where n is equal to j. For all other values of n, when n is not equal to j, this overlap will become 0 and the term will become 0. So, therefore, I am left with one term, that is C j multiplied by e to the power minus I omega j t 0. So, this is the term that I am getting. So, now let us see what is in the right hand side. I have in the right hand side C j, the coefficient, multiplied by this time factor, which has e to the power minus I omega j. Omega j is something that I know, and t 0 is the initial time. So, this quantity I know. So, therefore, I can write my C j as psi j star multiplied by e to the power I omega j t 0. So, this is the formula for my coefficients to obtain. How do I get this? So, I simply have these eigenfunctions, I know them because they are the solution of the time independent part, and this one is the total function or time dependent function at a time t equals 0. When I evaluate this overlap, I get some constants, then I multiplied by this time factor, and I have got this C j. And once I have this C j, then psi of x t is can be expressed as C n over this term multiplied by when I use this term over here, you would see I will have C n, which will have this term over here e to the power I omega j So, I have e to the power I minus I omega n t, and this is t 0. So, this will give me e to the power minus I omega n t 0 t minus t 0, because I have this minus sign over here, multiplied by psi n of x. So, now what I am getting psi x of t as this term multiplied by psi n x. So, now I exactly know how to get these coefficients, and once I get this coefficient, the probability density would come out naturally. So, we discussed about the stationary state and the non-stationary state. Now, we will discuss one important property is that the energy time uncertainty. When we are discussing uncertainty principle, we said that there is a position momentum uncertainty. So, for example, we said that position and momentum they do not commute with each other. So, therefore, we cannot simultaneously and precisely measure x and p x. So, this is the famous position momentum uncertainty. Similarly, we have also something called energy time uncertainty. Now, the point is we know that energy corresponds to the observable corresponding to the Hamiltonian operator. But what about the time? When we look at this energy time uncertainty, suppose we have this time over here, I would say that since my Hamiltonian is independent of time, so therefore, this would commute because they have two different they depend on two different variables, but this would be actually an incorrect way to put it. When we discuss about time and energy time uncertainty, we must remember that time is actually not an observable. We said that while discussing the postulates of quantum mechanics, for every classical observable there exists a time there exists an operator in quantum mechanics. However, time is actually not an observable, rather it is actually a parameter. A parameter or a variable that changes, and then other observable changes accordingly. So, time is, since time is not an observable, we do not have so called a time operator to check its commutation. So, therefore, this interpretation of energy time uncertainty is incorrect. What is then this energy time uncertainty. So, when I have position momentum uncertainty, I said that delta x into delta p x is greater than or equal to h bar by 2. Similarly, the energy time uncertainty tells me delta E delta t is greater than or equal to h bar over 2. So, this delta E is the uncertainty in energy, which are actually the observable corresponding to the Hamiltonian operator. What about delta t? Delta t is not expressed as we have expressed in delta t, that means it is not an ensemble average of t, rather it has a different meaning. We saw that when the system is a stationary state, its probability density is independent of time, but when it is non-stationary state, this term had explicit dependence on time, whereas for non-stationary state there was no explicit dependence on time, rather it was independent of time. Now, where did we get non-stationary state? We obtained non-stationary state when the wave function, the state function, is not an eigenfunction of the Hamiltonian. When the state function is not an eigenfunction of the Hamiltonian, we express the state function as a linear combination of several eigenfunctions. And when we express the state function as a linear combination of several eigenfunctions, therefore, when we make a measurement of energy, we do not have a precise value of energy, rather we have a distribution of energy, and that distribution gives us an uncertainty in energy. What about stationary state? The stationary state is obtained when the state is an eigenfunction of the Hamiltonian, the time independent Hamiltonian, and when the state is an eigenfunction, it has a definite energy, and that energy is suppose E n, and no matter how many times how many systems I prepare and make that energy measurement, every time I will get only one value of E n, and therefore, the uncertainty becomes 0. So, there is no uncertainty in energy for a stationary state. On the other hand, for a non-stationary state, I have an uncertainty in measuring energy. When I am in stationary state and there is no uncertainty in energy, so therefore, the delta t, which is now the lifetime of the state, is actually very large. So, when this uncertainty is very small, delta t, that the lifetime of the state is very large. So, that means the stationary states have in principle infinite lifetime, that means they are very stable and they remain so. On the other hand, the non-stationary states, since there is a spread of energy, so that and there is a delta E becomes finite, so delta t also is lower. So, therefore, when I have a non-stationary state, the energy uncertainty increases. So, therefore, the lifetime of the system, lifetime of the state decreases. So, this is the physical significance of this energy time uncertainty. Let us now discuss the time evolution of the expectation value. For that, let us say let us define an operator omega operator, which does not have explicit time dependence. So, this operator, this is very important, this operator does not have explicit time dependence. What is its expectation value? Its expectation value is given by this. So, whose expression is that if the system is in psi, so I have psi star omega psi d tau. So, this is the average value or the expectation value corresponding to this operator omega. Now, the question that I am asking is that how does this change? How does this expectation value change with the time? When I would want to do this, I would do a time derivative on both left hand side and right hand side. So, I did that for the left hand side. Now, I look at the right hand side. So, in the right hand side I have this integral where I have three terms psi star omega psi. So, psi star has the wave function has explicit time dependence, we know that now, and the operator we have defined which has no time dependence per se, no explicit time dependence. So, in that case I can write this as the first term plus the second term and I am not writing the term where I am trying to differentiate the operator, that is because the operator is independent of time, does not have explicit time dependence. So, in this case I look at this the first term, and here it is written that the time dependent Schrodinger equation is written down. So, you see the d psi by dt is 1 over I h bar into h psi, but I have now the complex conjugate of this function. So, therefore, what I have here so, I simply used this relation over here. Again the same relation I would use in this case. So, d psi by dt I just take 1 over I h bar outside, and then I am left with h psi. Now, I have this term minus and let us take 1 over minus 1 over I h bar outside. So, here when I see this term, I use the Hermitian nature of the Hamiltonian. The Hamiltonian is Hermitian. So, therefore, I can write this in this way. Now, you see I have two integrals over here. Here you would see that these are the two operators, and the functions are actually same in both cases. So, I take them now. You see when you look carefully, you would see that this is like a b minus b a. So, I can rewrite this. I am instead of writing 1 over minus 1 over I am writing now I divided by h bar. So, this is nothing but the commutation of h and omega operator, and when I have this operator over here. So, this term simply indicates the expectation value of an operator, and what is this operator? This operator is the commutation of the Hamiltonian and this omega, where omega is an arbitrary is an operator whose time evolution of its expectation value I am interested in. So, I see that the time evolution of this expectation value of an operator is given by this term in the right hand side, which says that first find out the commutator between the Hamiltonian and that particular operator that you are interested in, and then find out its expectation value and multiply it with I over h bar. Now, suppose there is an operator which commutes with Hamiltonian. So, if an operator that commutes with the Hamiltonian, so in that case this commutator becomes 0. So, average value of 0 is anyway 0. So, in that case if omega commutes with Hamiltonian, so I have d over dt expectation value of omega is 0. So, that means the average value of this operator, the expectation value of this operator does not have a time dependence. So, therefore, this is called a constant of motion. That is possible, that is true when the operator that I am interested in, if it commutes with Hamiltonian. If there is an operator that commutes with the Hamiltonian, then I know that its expectation value will not change with time. This is an important result that we would use it in the next discussion. Now, we will use this relation that we derived in the previous slide, and we would try to do this, find out what is the time evolution of expectation value of the linear momentum operator. What is it? To do this, first I have to, since I am interested now, this is my omega. So, I would first evaluate what is the commutator between the Hamiltonian and the linear momentum. So, the Hamiltonian will have a kinetic energy term plus a potential energy term, and I know I can write this commutator as sum of the two commutation. First one will be p square with p, and that will become 0. So, I am left with the commutation of V, the potential energy operator, and the linear momentum operator. And now I use the linear momentum operator. So, you see this is minus I h bar d by dx. This is constant, so I brought it out. So, now let us look at what is the commutation between V and. So, to when I evaluate this commutator, I must, because this is an operator, so I must use a function. So, the result of this is a b on the function minus b a on the function So, this would give me the first two terms cancel out, this will give me and therefore, when I write down the only the commutator, I would simply write minus I h bar minus sign d v by d x, which is nothing but I h bar d v by d x. Now, this is the commutator between Hamiltonian and P x. Now, what is the time evolution? So, this one would turn out to be I divided by h bar multiplied by the expectation value of this quantity. So, let us see. So, I h bar, they are constant. So, I am bringing them out from the expectation value. So, I would give minus 1, h bar will cancel out. So, I am left with so V is the potential energy operator, and I know the negative gradient of potential energy with respect to the position is the force. So, therefore, what I have in the right hand side is the time evolution of the expectation value of P x is nothing but the expectation value of the force. So, if you see here, what does it tell? That the time average evolution of the time derivative of the linear momentum is force. So, this is one known as Ahern-Fest theorem, and this should remind you with Newton's equation of motion, which tells about F equals m a. Now, we would look at another quantity. We would see how the time evolution of position operator behaves. So, to do this, again, since I am interested in the time evolution of the position operator. So, first step is I must find out what is the commutator between the Hamiltonian and the position operator. So, I know the Hamiltonian operator has two terms. So, these are all operators. So, I write down first the commutation with the momentum square with x plus v with x. Since v, if I evaluate this commutation, I would see v x minus x v, which are both have multiplicative in nature. So, therefore, this becomes 0, and I am left with only one term over here, 1 over 2 m p x square x. Now, I have to evaluate this term p x square with x. So, I would do that by using the product rule that we discussed in a few classes before. So, I take this, I am treating this as a b. So, I take a outside and then do b with x. Now, when I look at this p x x, I already know that that is minus I h bar p x, and this will also be minus I h bar p x. So, that will give me minus 2 I h bar p x. Now, this is the commutation of between p x square and x. So, now when I put this result over here, I am left with minus 2 I h bar divided by 2 m p x. So, which is nothing but sorry that is, this is what I have now. Now, to obtain this, I would use I divided by h bar multiplied by minus excuse me multiplied by minus I h bar divided by p m and expectation value of p x operator. Since these are all constants, so I brought them out of the expectation value. So, when I look at this term minus I become 1, h bar they cancel out, then I am left with 1 over m. So, I can rearrange this equation as this should remind you the mass multiplied by the time derivative of position, which is velocity, gives to momentum. So, this is again reproduces the classical relation that we are so familiar with. So, if we take them together, we have now these two terms which tells the time derivative of linear momentum is the force and mass into velocity is the linear momentum. So, these two equations closely resemble the classical equations of motion, and they in quantum mechanical sense are known as Ahern theorems. So, in today's lecture we discussed about the time evolution of the expectation value of an operator, where the operator does not have any explicit dependence on the time and by using the time evolution of the expectation value of momentum and position operator, we derived Ahern theorems which closely resemble to the classical equation of motion that we are so familiar with. Thank you for your attention.